So we've moved on to dynamics, really the second main section of mechanics, and dynamics being the study of forces and their effects. So we need to understand a little bit about Newton's three laws. First of all, Newton's three laws, the first one really involves objects remaining stationary or at a constant speed. Unless they're acted upon by an unbalanced force, then they'll remain stationary or they will remain at a constant speed. If you're dealing with Newton's second law, then you're dealing with unbalanced forces. And the gist of that law is that unbalanced forces cause acceleration. So if an object is accelerating, then it will have an unbalanced force in that particular direction. Newton's third law, slightly more complicated, but we'll look at it a wee bit later, is action and reaction pairs. So for every action force, there's an equal and opposite reaction force. So we're getting used to drawing out free body diagrams. So we started off with a really simple question where we calculate the acceleration of a car of mass 900 kilograms. We're given an engine force, which is obviously going forwards, and we're given a frictional force which acts against the motion. So for a free body diagram, the first thing we do is we draw a little box. We don't bother drawing out anything fancy or taking ages over our diagrams. We just draw a little box. We write in that what the mass is of the object. Then we indicate the forces acting. So the forward force is 10,000 newtons. The force acting against the motion, friction, always acts against the motion, due to things like air resistance and friction between the tyres and the road, always acts against the motion. So we know therefore that there's more force going this way, so we say that the unbalanced force goes in the forwards direction. The next thing we do is then apply our equation. We calculate out what that unbalanced force is. It's 5,000 newtons going to the right. We then apply Newton's second law because we're looking at unbalanced forces. Newton's second law tells us that F equals ma. So what we used here was a rearrangement of that equation. This F, remember, is your unbalanced force. We calculate out that acceleration is 5.55 meters per second squared. We then look at a second example that is slightly more complicated, but we use the same free body diagram arrangement. We lay things out in exactly the same way. So a liquid fueled rocket takes off from the moon vertically upwards with an engine thrust of 120,000 newtons. If the weight is 40,000 newtons, calculate a few things there. Initial acceleration, figure out what the acceleration does over time, and would this rocket take off in it? So we start off with the same stuff. We don't know the mass this time, so we haven't written that in here, but we've just drawn a box. We've indicated the thrust acting upwards, the weight acting downwards, then calculated what that unbalanced force is over here. Use that unbalanced force along with mass, which we can calculate using W equals mg. Remember, weight is the force that acts upon an object due to its mass and due to the gravitational field strength. And mass is just how much stuff is inside something. We use that to calculate acceleration. For a rocket, we decided that the acceleration would increase as it begins to rise because of two things. The first thing, as the height increases, the weight becomes smaller, so therefore the unbalanced force in the upwards direction is bigger, so therefore acceleration is bigger, because if you've got unbalanced force in the upwards direction, then you've also got an acceleration in the upwards direction as well. Secondly, because the fuel burns, mass decreases, so it's therefore easier to accelerate an object in the upwards direction. For the object on Earth, we had to recalculate what the weight was because we've got 9.8 newtons per kilogram of force acting down the way as opposed to 1.6 on the moon. So we calculate out that weight is in fact much bigger, 245,000. So weight's far bigger than thrust. We can see that the unbalanced force is then in the downwards direction. So if weight is greater than thrust, then unbalanced force must be downwards and the rocket cannot take off. So we lay out these free body diagrams in the same way all the time. We draw a diagram. First of all, we mark in what the masses are. We mark in any sort of forces that might be acting on the object, up or down, or left or right. We can then decide whichever direction the unbalanced force is going in. And then if there is an unbalanced force, then we need to do a calculation, and we use F equals ma in order to do that. But we must calculate what the unbalanced force is first, so we need to calculate what the resultant of these two forces is in order to do that.